This is the first tutorial on the topic mole concept in stoichiometry. I think it's one of the first chapters you do in chemistry in class 10, and so it's also one of the most important. The first thing, I'm going to start off with Gay-Lussac's law of combining volumes. I'm going to go quickly through it because it's pretty easy actually, and it's all given in your books pretty clearly. So I think the best source to understand that would be, of course, after your teachers, you should go to your book and then come here. So I'm just going to do it very, very quickly. Uh, it's a law of combining volumes. I'm going to do it with a small example. So basically, let's take N2, which is nitrogen, plus H2, which is hydrogen, combines to give you ammonia, which is NH3. Now, since class 7, you've been learning how to balance these type of equations. So when we balance it over here, what we get is 2 over here, and we get a 3 over here. Yes, that's balanced. So now if you look at the ratio, this is actually 1 and 2. It means the same thing. So now if you look at the ratios of the 3, you could write this as 1 is to 3 is to 2. So this is, the law just says that, say you have um, say you have one V of, say you have just this flask which is of a standard size, and you fill N2 in it. You take one of these. After that, you take 3 of these flasks, same flask, exact same flask, fill it up with H2, each of them with H2. What you will get is equivalent to 2 flasks of, again, the same size, of NH3. That's all it really says. And to put it as a definition, it would be the law that whenever gases combine, they do so in volumes which bear a simple whole number ratio to each other, as well as to the product if it is gaseous under the same condition of temperature and pressure. It sounds very big, but the first part says that when two gases combine, I'm going to use a different color here. Okay, so when two gases combine, now in our example, the two gases combining are N2 and H2. When two gases combine, they do so in volumes. Now these volumes are these, which bear a simple whole number ratio to each other. The whole number ratio is here. So say the volumes would be, you could take 1 liter and 3 liters, or you could take 2 liters, make this 2 liters, and make this and 6 liters. So basically, whenever it'll combine, the ratio will be 1 is to 3, and that is a simple whole number ratio, which means that you won't get a ratio like half is to 1. You, instead of half is to 1, it's the same as 1 is to 2. So whole number ratio to each other, as well as the product if gaseous. Now the product will also take part in this whole law only if it is gaseous, and you know from your previous chapters that ammonia is a gas, so this law applies to this as well. This is the product. So now you look at the whole number ratio of ammonia as well. So that is 2, and again it's whole numbers, that verifies the law here. Under the same conditions of temperature and pressure, this you need not worry about it. At your level, uh, it's assumed that there is standard temperature and pressure, so just learn that in the law, but no need to, think about what will happen if they're not the same conditions of temperature and pressure. So that's basically the law. It's pretty easy. 1 flask here, 3 flasks here, give 2 flasks over here. That's it in this law. You'll be using this in in the mole concept as well. Now, also keep in mind that none of this is applicable to solids, liquids. This is all to do with gases. Uh, it will, if you have two reactants here which are gaseous, it will apply to them. And say that this product here formed is, say it's a liquid. So in that case, you will only take this part and not this part. Right, so that's it for Gay-Lussac's law. Now we come to atomic weight. I'm just gonna erase this first. Atomic weight, you would have done in several other chapters. You've been doing that since class 7 when you started chemistry. Let's take a different color. Okay, atomic weight. Go and write AW. Atomic weight is basically, you take any one element. Let's say we take hydrogen over here in this example. One atom of hydrogen, we know from the periodic table that it weighs 1 AMU. Now how do we know this? This is how atomic weight is really derived. Atomic weight is defined as the number which represents how many times one atom of a substance is heavier than 1/12 the mass of an atom of carbon 12. Carbon 12. Now carbon 12 has 6 protons, 6 electrons, 6 neutrons. Now electrons' mass is considered negligible compared to these two, so we only take into account these two when we're finding mass of any element, in fact. So usually proton and neutron's mass is considered just about the same. There's very little difference. So if you take 6 plus 6, we take 12 over here, and we put the unit as AMU, which is atomic mass unit. Now 1/12 of 12 would be 1, of course. Now also note that these are all approximates. Actually, this value will not be exactly 12. Uh, so yeah, but at your level, no need to go into that. So you have 1 over here. So all they're asking, all that atomic weight tells you, is that one atom of any substance, how many AMU does it weigh? Which means that how many protons plus neutrons does it have? Hydrogen has just the 1 proton and it has 0 neutrons. If we take helium, helium has 2 protons and 2 neutrons. So its atomic weight is 4 AMU. 4 AMU. Sorry, that doesn't look like AMU at all, but I'm out of space. Okay, molecular weight. Firstly, difference between a molecule and an atom. You should know this by now, but atomic, the word refers to any one element. So, say you have examples would be H, He. You could have lithium, say Zn, copper, iron, oxygen, nitrogen. You could go on like this. Now if you talk about atomic weight, you're talking about each of these. It's not O2, it's just O over here in atomic weight. Now if you talk about molecular weight just refers to any compound's weight. Now wherever there is a bond, then you take molecular weight. So for example, O2 is a molecule. because you have two O's bounded together via this covalent bond in the middle here, and this will be a molecule. So if you're told to calculate the molecular weight of O2, then that will be, it'll actually be 32, because the atomic weight of O is 16, and so you just do 16 into 2, 32 AMU. Same way, say we take ZnCl2. This will not have atomic weight, it will definitely have molecular weight. So if they ask you to find the atomic weight of ZnCl, sorry I missed out the 2, ZnCl2, then that's really just an invalid question. You can't do anything about that. Okay, that's it under atomic and molecular weight. Now, also when you express any, suppose you express molecular weight in grams, it's called gram molecular weight. You'll see more of that later. Now we come to the most important part of the chapter, Avogadro's law. Now, before I move on, I'm gonna clear this. So, Avogadro, he's the one who introduced mole concept. So his theory suggested that under similar conditions of temperature and pressure, similar, then when you take um, any equal volume of any two gases, or any more than two gases also, they all will contain equal number of molecules. So equal volumes of all gases contain equal number of molecules. So say I take 1 liter of O2, I take 1 liter of N2, I take 1 liter of let's say Cl2, and you could go on like this, just take 1 liter of every gas. All of these would have the same number of molecules. It's not moles, it's molecules. Okay, so now also it was also found out that at STP, 1 mole of any gas, whether it's O2, N2, Cl2, or any other gas, the volume that it occupies is called molar volume. And this value is fixed at 22.4 liters. So you can see from this relation that if you take say 22.4 liters of all gases, instead of just one here, you take 22.4. Just imagine, I'm not writing all of them, I'm just writing 22 here. Say you take 22.4 liters of all of them. You would, from the relation above over here, you know that you've taken 1 mole of all of these gases, and then this relation over here tells you that all of these 1 mole of all of these gases contain the same number of molecules. So that obviously means that every mole of a gas contains the same number of molecules, and this number was called Avogadro's number, and that is 6.023 into 10 power 23. Might seem a little tough at first, but once you start reading more often, you'll get used to it. And actually, in next year, you'll actually start using, for some reason, you'll start using 6.022. That's the correct value, but in all your class 10 books, it says 6.023, so you should stick by it at least for now. Okay, so now also how to calculate how many moles are there. Now, 1 mole of any substance, let's take just calcium, or let's take, just to start off, let's take hydrogen. Let's take H2 rather. So 1 mole of hydrogen will weigh a certain amount. All you need to do is find its molecular weight. Since it's a molecule over here, its molecular weight comes out to be 2 AMU. All you do is can just write this AMU as grams. So 2 grams is the molar mass. That's it. That's how much 1 mole of H2 weighs. Similarly, we can do 1 mole CaCO3. Now I remember the values of this because once you start doing the sums, um, you'll automatically remember most of the weights. So this is 100 AMU. Just to confirm, this is 4803. You add 1260 and CS40. Yes, 100 AMU. And so the molar mass of CaCO3 is 100 grams. So now you can link this up. If you take 100 grams of CaCO3, you'll have 1 mole. And of course, if you have 1 mole, you'll have 6.023 into 10 power 23 molecules. So you know that if you're holding 100 grams of CaCO3, you can easily know how many molecules you're holding. So I think that's it for this now. Um, also, if you're given, say, if you need to find the number of moles in a given sample, let's take CaCO3 again. Let's say you're given 150 grams and you've been told to find the number of molecules in it of CaCO3. Now 150 grams, you can see that uh, you know from here that 100 grams is 1 mole. 100 grams is 1 mole. So now you've been given 150. So how many moles? So just cross multiply, do by unitary method. You get 150 by 100, which is of course 1.5. So you know that you have 1.5 moles. 1.5 moles. And now you also know that uh, 1 mole contains Avogadro's number. This over here is called Avogadro's number. It contains Avogadro's number of molecules. So easily again by unitary method, you can find out that how much is 1.5 have. So 6.023, this whole thing will be upon 1.5. And in some of the sums, it'll be specified that you could take the 6.023 simply as a 6 just to simplify calculations. And actually you should know that in chem, what they normally test is not your math but your chemical concepts. So usually if you look out, you'll see that most of the things will cancel most of the time. So we can just write this as a 4, and so we get 4 into 10 power 23 molecules. um that's it for this video. I'm going to continue this in the next video, where we're going to do vapor density, percentage composition, and empirical formula. We'll see in the next video.